Friday slightly even though it's also an emulation like so really I should have not really box size.
Okay, we've learned that matrices are incredibly important in linear algebra because they define linear transformation in a certain sense. That is to say, multiplication by a matrix gives you a linear transformation, and not only that, any linear transformation from Rn to Rm can be written as a matrix. And so we're going to talk about some operations. Some of this I've already told you about, but it's not going to hurt to kind of see it from another point of view. My notation here. So this is a M row in column matrix. I might write it this way. Where these are column vectors, all of these will be M high because I've got M rows and then I've got M columns. Or I might write it Aij. And this is to sort of denote matrices like this, A11, A12, 21, 22. Well, this notation means the IJ entry, right? So Aij is, in general, the entry in the ith row, I down, j column, j over to the right. Okay. The diagonal of a matrix are the entries A11, A22, however many is appropriate. So for example, if I have the following matrix, this is a 4 by 5 matrix, right? I've got 4 rows and 5 columns. The diagonal entries are first row, first column, second row, second column, third row, third column, fourth row, fourth column. There is no diagonal entry corresponding to this last column because the matrix is too short, right? Or if I had one like this, then the diagonal entries would be 1, 6. First row, first column, second row, second column. You just do this until you run out of space, right? And this one doesn't, this row doesn't have diagonal entry because the matrix is too tall and skinny. Okay. A matrix A is diagonal if, now for a matrix to be diagonal, I am going to demand a few things of it. Number one, A is a square matrix. So that is to say A is an R in by N. So the number of rows and the number of columns are equal. That's not good enough. Not just square, but all entries not on diagonal are 0. So if you're not on the diagonal, you're 0. So for example, here's some diagonal matrices. That's diagonal. It's true. All you really need is the entries off the diagonal to be 0. The entries on the diagonal are 0 too. I didn't make any restrictions on that. Or 1, 0, 0, 2, that's diagonal. Or 3, 0, 0, 0, 0, 0, 0, 0, 4. These are all diagonal metrics because everything's off the diagonal is 0. Diagonal matrices are going to actually come up. Notice that the matrix of all zeros is a diagonal matrix, and so is what do we call this matrix?
Priorities echelon. That's
Right, it is in row one, absolutely, but it's a special kind.
it's the statement.
This is the identity matrix. In particular, it's the 4 by 4 identity matrix. The identity matrix is a diagonal matrix. So that's an important piece. Let me give you another definition. Two vectors are equal. We say they're equal if they're the same size and they have the same entries corresponding, right? It's the same thing for vectors. We say the matrices A and B are equal if, number one, well, actually, let me, in my definition here, let me write this out just a little bit more dramatically. So here's my sort of entries notation for a matrix, if you will. If these two, number one, A and B are the same size, that is, the number of rows and columns from A and B turn out to be the same. And number two, Aij, Ij. So in other words, if you compare the entries, you get the same thing. So two matrices are the same. I think it's exactly what you would hope it to be. We say they're the same if they're the same size and the entries are the same. Plain and simple. Okay. Yeah. If I have some m by n matrix A, m rows, n columns, and lambda is just some number. I can multiply any matrix by this number. What do you suppose I do? In fact, maybe a numerical example will help us. What if I have 4 times the matrix 1, 0, 1, 0, 2, 1, 4, 3, 7, 2, 5, 6. What do you want 4 times that to be?
4 times everything.
Your wish is my command. That's exactly right. I mean, that's the most logical thing. Remember, this is a little bit facetious, but in math, if it ain't easy, don't do it, right? Do the most natural thing. 4 times everything in there, right? That's what we're going to do. 4, 0, 4, 0, 8, 4, 16, 12, 28, 8, 20, 24. There we go. That's the way I would want to multiply a number by a matrix. So let me write a formula for you here. What did I do? Well, I just took every entry and I multiplied by the number. And there we go. This is what I think you would hope for it to be. Let me ask you another question with a kind of a numerical motivation. I want to make a new matrix by adding these two. What's the most natural way to do this?
Add each element.
Add it position by position, right? 8, 1, 9, 1, -2. Okay. Right away, I think that's completely logical. You should add then piece by piece, every sort of coordinate matrix, if you will, every entry, add it up. But what is implicit in this? What do I need to be able to add matrices up?
They're the same size.
You need for them to be the same size. I'm not going to define, how do I add a 2 by 2 matrix to a 5 by 3 matrix? I can't really. So we're not going to pay any attention to that. So if A and B are both in R n by n, that is to say they're the same size, or n by n, they're the same size, and A is Aij and B is Bij, then I'm going to define A plus B to be the matrix Aij plus B. And this just means add up the matching entries. That's it, just like what we did. Okay, any questions? So let me give you a theorem. I don't think this is going to be a surprise to anybody. Theorem. Let A, B, C, A, B, C being on. So what I mean by this first statement is A, B, and C are all the same size. And I'm going to let, let's throw some Greek letters at this so we can do really important. Let alpha and beta be just two numbers. Here are some rules about adding matrices and multiplying. This is equal to B plus A. Because remember, every entry is just a number. Does it matter what order you add numbers in? No, 2 plus 5, 5 plus 2, same thing. So this translates over to matrices. 2, A plus B plus C. And again, this is because adding numbers is associative. So if you've got to add 3 matrices up, it doesn't matter if you add the first 2 first and add it to the third, or take the first one and add it to the sum of the second 2. It's all the same. 3, A plus. By the way, what do you suppose I mean by 0 with that hat on it?
0 vector.
Right, and in this case, the 0 matrix, right? So 0 bar is M by N matrix with all zeros. This is what we call the 0 matrix. Or if I multiply a number by a sum of 2 matrices, what do you hope that turns out to be?
Alpha A plus alpha B.
I certainly do. And that's exactly what it turns out to be. And what's good for the goose is good for the gander. That is to say, if I have alpha plus beta times A, right, these are 2 numbers. This is alpha A plus beta A. And finally, one last one. Number 6, alpha times beta A is the same thing as alpha beta first times A. So if you take the matrix A and you multiply it by some number beta, and then multiply that whole number, some number alpha, it's the same thing as just taking the original A and multiplying by alpha times beta. So you would hope things work out that way, and they. All right. Now, any questions on this? Okay, so what about that? Well, we talked about adding matrices. No surprises, they got to be the same size. I've talked about multiplying a matrix by a number. No surprise that you just multiply the number all the way through the matrix. And here's some rules they follow, and these are rules just like ordinary numbers follow, which is good. We've also talked about multiplying matrices. So let's kind of revisit this. And I've told you all how to do this. And so we can compare this with some other viewpoints on the subject. So first question. So suppose that I can multiply, I can do this multiplication anytime. What can you tell me about this?
And it has an n number of rooms.
Okay. I don't know what K is, could be about anything, but I know that you must match here. What if now what do you know?
C has to have a m number of rooms. No.
Columns, all right?
Yeah.
Because at M, if I'm gonna multiply C on the left side of A, that M has to match that M. Okay. So let me point out, this is kind of weird, but if I can find BA, it doesn't necessarily mean I can find BA, right? AB exists because B has n columns. The only way I can multiply it the other way is if K happens to be M, right? Do I agree with them? So, let's suppose that A, so I'm going to multiply it in order AB. Of course, everything applies in equal order. And let's say B is an RK, R n by K, we can multiply it. And I'm going to do a short example just to kind of remind us, and I'm going to refer back to the example when I talk about some other stuff. So let's look at this example right here. Suppose A is and B is now multiply these in both orders. Yes, I can. This is what, 2 by 3, and this is 3 by 2, so I could do this in either order. But I got lucky. Somebody tell me what the size of AB is. Good, it's 2 by 2, because this is 2 by 3. 3 by 2. By the way, it's interesting to note that if I multiply them in the other order, I can do that, right? But when I multiply them in the other order, it's not even the same size, right? It's 3 by 3 in the other order. So there's no way AB and BA can't even do the same thing. They're not even the same size, right? So can anybody put their eyeballs on this and tell me what is the first row, first column entry of AB?
16.
Agreed. 3, 3, 10. How about the next? How about first row, second column?
-18.
Probably. First row comes second column, -3, -15 is my. Second row, first column, multiply second row by first column, 4 and 6 looks like it's 10. And second row, second column looks like -4. Okay, so that's kind of a blast from the past, but let's think about this in some other ways that might give us some other insights. My way is sort of a quick computation way, I think, the product of matrices. However, you can also think of it this way. If you write B in its column vector form, let's say this is B1, B2. By the way, what should my end game be? That is, so you guys know what I'm doing here, right? Instead of B, I'm gonna write as columns, B1, B2, all the way to B, B what?
Okay.
B, very good, because B has 8 columns. Multiplying this, we've kind of seen before, this is just basically taking a matrix times a bunch of column vectors. So this is A, B1, A, B2, all the way up to A, BA. Now, first question is, how tall are the columns here? These BI columns that I put in, how tall are they? Right. These are all n tall, right? These are column vectors within interest. How tall are these? Yeah, I think they're n tall. There's a couple of hints to this, right? When I take A times B, I should get an n by k. Right, which means that I've got n rows, so these should be n tall. Another thing is if I take A here and I multiply it by n by 1 vector, remember these are all n tall. This little thing in here is m by n, and this vector right here is n by 1. So these should be n tall. Note each column of AB is a linear combination of the columns of. Using appropriate column of B weights. Now, let me go back to this example here and try to show you what I mean by that statement. What do I mean by linear combination of columns of A? So let's see what we've done here. The columns of A what are they? They are 3, 4. They're the vector 1, 2, and the vector 5, 0. Everybody okay with that? So I'll just pluck off the columns of A. The columns of A, B, right? So this is my bold statement here. I said the columns of A, B are some linear combination of columns of A. What are the columns of A, B here?
16, 0, 18, -4. Now, let's see what happens when I do, and notice this is the column, this is B1 vector, first column B, B2 vector. So if you look at A, B1, which should be the first column of AB, you'll see what this is. This is A times the first column of B times B1, which is 1, 3, 2. And if you multiply A by 1, 3, 2, well, what do we get? Well, we get 3, 4. Let me put a 1 there for emphasis. Plus 3 times 1, 2 plus 2 times 5. Because, for example, the first entry, so if you look at the column of B, you get this times this, and so, and then you get this times this. So the first entry in the column is, notice you're multiplying 1 every time at the beginning of the column, 3 times this and 4 times this. So it's 1 times 3, 4, this first column. And then it's going to be 3 second weight times the second column, and then 2 times the last column. And let's make sure that this comes out the way it should. This is the vector. 3 and 3 is 6, and 10 is 16. This is 4 and 6 is 10. I'll do 10. There we go. If you look at A, B2, this is A times -1, 0, -3. So I get -1 times 3, 4, plus 0 times 1, 2, minus 3 times 5, 2, which equals -3, -15 is -18, and -4, 0, 0. So that's what I mean by that statement. Notice what we're doing is the columns of the new matrix are linear combinations of the columns of what's on the left using these weights going down. Okay, any questions on this? Does everybody remember in calculus what function composition is? Right? If you remember these kind of questions, that's probably maybe in a pre-calculus class. You might have gotten something like this.
You guys remember doing this kind of crap with in calculus, right? And this was like f of g of x, which, by the way, what is f of g of x in this case? Yeah, that's right. So this would technically, this is f of sine x. And what does f say? F says, hey, take my x and square it. Well, in this case, my x is sine x. So that's what it is. And this, the more popular notation for this is that. Agreed? What about the other way? This time, what's inside the parentheses is x squared. So this is sine of x squared. Are these functions the same? Can you prove it for me?
Well, in a very practical sense.
I'm good with practical.
If you type it into a CAS calculator and set them equal to each other, it will say false.
Yeah, that's what you.
Okay.
Let me ask you this. What's the biggest function? What's the smallest? Zero, right? Because you're squaring something, right? No way this is ever negative. What about this one? Right? This can certainly be negative, right? Notice that, for example, the sine of 3 pi over 2 is -1, right? Just take x to be the square root of that, and it squares it out and get negative. So these two things are actually quite different, right? So what is your instructor having a stroke up here? Why am I all of a sudden talking about this crap? Well, because there's a connection with what we talked about matrix multiplication. And that is when you multiply two matrices, like we've been doing, this is what you're doing. You're doing function composition. So let me kind of demonstrate this. Let's suppose that we have let's say T goes from Rn to Rn. And let's suppose a linear transformation S goes from, where do I want to go? Right. So we'll say that this is okay. So suppose I've got these two linear transformations. T goes from Rn to Rm, and then S goes from Rk to Rn. Okay. We'll say that this is represented by A. Because remember, this is one of the big things that we have before is we can have any linear transformation can be written as a matrix, right? What's the size of my A? It could be n by n. Because what A is supposed to do is it's supposed to take an n by 1 vector and barf out an n by 1 vector, right? And so if this is n times n times 1, it will spit out an n by 1 vector. So starts in Rn and ends in Rn. Everybody agree? I know it looks a little backwards, but that's the way it is. How about this? Where should that be if we follow the pattern? That is correct. Right? Because what happens here is you put in a k by 1 vector. So you start here, and it should barf out an n by 1 vector. End up here. So we can multiply these two matrices. Which order does it? Which is the order that you're guaranteed being able to multiply?
A times B.
We can multiply and get AB, because I know this is a tie. To multiply the other way, what do you need to happen? What has to happen to be able to multiply in the other direction? M and K have to be the same thing. Everybody okay with that? So this should be in AB should be where?
And M by K.
Okay. So what does this have to do with linear transformations? Well, here's what's happened. So what happens here? S takes an input vector from RK and it spits out something in Rn. And P takes an input here and spits out this. So if I start with a vector here, what's the little path of the vector here? When you look at S of V, this should be in Rn, right? And now you do T to it. And this is T of S. V. And this now should be in Rn. Everybody okay with that? Any questions on that? So notice that when you do this is S composed of T. You do S first, then you compose T, and this gives you a linear transformation from K to M. And what do you suppose that this T composed of S is represented by? You're supposed to matrix it. B goes to AB, right? Notice B, what does B do? It takes the K by 1 vector and it turns it into an N by 1 vector. And then when you do A to it, it takes the N by 1 and turns it into an N by 1. So it gets you exactly where you want to go. So for a concrete example of this, let's let B equal 2, 1, 1, 4. Let A equal, let's see. Three by two, 2 by 2. Right. So if you look at somebody give me a 2 by 1. Give me a 2 by 1. Yeah, sure.
13 cents.
13 cents. What happens if we multiply this by B? So that's a linear transformation. This will take this to R2 as well. Two, 1, 1, 4, 13, 7. BV is this. Well, this is 26 and 7 is 33. And this is 13 and 28, which is. And now, if you look at ABC. This is whatever that A was, 3, 1, minus 1, 2, 5 minus 4. Comes the vector, whatever I ended up with, 33.1. What do I get now? Well, I should get, since this is a 2 by, this is a 3 by 2, and this is 2 by 2, I should give a 3 by 1 matrix, right? So this is 99 and 41, it's 140. This is 82 minus 33, which is 49, I guess. Yes. And this is 165 minus 164. Wow. You do that on purpose? It's a good shot. Okay, so notice that this is the same thing as AB. Because if you look at AB, let's just turn this into one giant 1, 5 minus 4. And let's at this point I'll say a little prayer that I've got with computation for us. So like a door. This should be a 3 by 2 matrix as well. Right? This is 6 and 1 is 7. This is 3 and 4. 6, 1, 7, 3 and 4, 7, like that. Yes, there you go. That's minus 2 and 2, 0. That is minus 1 and 8 is 7. 7 is in this. And this is 10 minus 4 is 6. And this is 5 minus 16 is minus 11. And so if I look at A, B, B, this is 7, 7, 0, 7, 6 minus 11 times my original 13 is 7. And that is 20 times 7, which is 140. This is 49. And this is 78 minus 77. So in particular, the linear transformation you get by looking at AB, you multiply that as a single matrix and do it here. It was much easier to figure out this matrix and multiply by this vector than you did the other one, several steps, right? And also the multiplications turned out easier. Okay. Any questions on that? Okay, so let me give you a couple of theorems to kind of round things out here. Suppose all multiplications and additions make sense. That is to say, suppose these matrices that I'm going to talk about in this theorem are all the appropriate size to do what we want to do here. Number one, AB times C is A times BC. And of course, what I mean is we're assuming that A, B, and C are all the appropriate sizes of this multiplication makes sense. 2, A times B plus C is AB plus AC. 3, B plus C times A is BA plus CA. D, if lambda is a real number, so it's just some number, then lambda AB
is lambda times A times B, which is A times lambda B. So in other words, you can multiply lambda by the whole product matrix. You can multiply lambda by A and multiply by B, or multiply lambda by B first, whatever you like. And E and here I'm assuming that A is in R in by A. So what this means is if you multiply this by the n by n identity matrix on the left or the n by n identity on the right to A, you get A back. Let me make the following marks, careful. In fact, you might not even be able to multiply them in other order. And even if you can, they're not necessarily equal. Also, see if you can find a simple example of this. Multiplying two matrices together and getting the zero matrix does not mean that either of the matrices have to be zero. You can multiply two non-zero matrices and sometimes get zero. In fact, you can square a 2 by 2 matrix and get zero. Now, there's one last thing that I need to talk to you about today. A equals Aij. It's transposed. We call, if you see that notation, A transpose, it's transpose is the matrix AJI. So for example, if A is 1, 2, 3, 4, 5, 6, then A transpose is 1, 3, 5. So notice you interchange the notion of row and column. The first row here is the first column here. Second row here is the second column here. Third row here is the third row here. First column here, first row here. That's what this means. I interchange every object with JI. So if A is in R m by n, then A transpose is in R n by n. And here are basic rules, and then we're out of here. Basic rule for transpose. Transpose A transpose is what happens if you transpose a matrix and then transpose it back? What do you suppose happens?
It's the same.
Good. Two. Plus B transpose is A transpose plus B transpose. Number 3. If you have a number times A transpose, a number times A transpose is that number times A transpose. And finally, see if you guys can tell me this one. What do you suppose that is? Any guesses? What is it? It's actually the order's reversed.
That's a little tricky, but I challenge you, go home and think about it. Assume that A is n by m, B is n by k. See that it has to be this way and make sure that you can multiply them right. So check that out, do an example. Any questions? All right, I will see you all on Wednesday.